A pleasant morning to all of you. The content I have chosen for today's presentation is Hamiltonian formulation. I am Dr. Ancemma Joseph, Assistant Professor, Department of Physics, Fatima College, Madurai. The learning objectives expected out of this presentation are information about configuration space and phase space, the conjugate momentum, how do we arrive at the Hamiltonian function, and a sample problem based on the conversion of Lagrangian to Hamiltonian. So what is configuration space? Any system, if you want to define the configuration at a particular instant, the instantaneous configuration is described by the values of the coordinates q1, q2 up to qn for n-dimensional system. It will correspond to a particular point in the hyperspace. Suppose I am taking a Cartesian space, two-dimensional space x and y defined by the axis x and y. The system configuration can be defined by a single point. Now at a particular time this is defined, and as the time goes on the state of the system changes, and again the system configuration can be described, and the point might have moved to another point t2 in the configuration space. So the path of the motion of the system can be traced by this curve. So this is called as the configuration space. So the n-dimensional space which will define the instantaneous situation or configuration of the system is called as the configuration space, where the coordinate axis will be the generalized coordinates, position coordinates. Now what is phase space? So now that we have seen what is configuration space, what could be the definition of a phase space? So the concept of phase space was developed in the late 19th century by Boltzmann for statistical mechanics. So then it was decoded by Gibbs and then Poincare. So in classical mechanics, we saw now that the configuration space is defined by the generalized coordinates q1, q2, and we will get the instantaneous position or configuration. So we may not get the details about its velocity from the configuration space, whereas the phase space is nothing but a space, again a hypothetical space, which will define all possible states of the physical system. We mean to say by all possible states the information about the position as well as momenta, we can derive it from the phase space. So how are we going to define this phase space? So the idea of phase space is very simple for classical systems. In configuration space, what we received was the information about the position. In order to get the information about the all possible states, in order to determine the future behavior of the system, we need to get the information about both the position as well as the momentum of the system. So as we plot the momentum of a particle as a function of its position, we end up with the phase space, phase plot. So it is a 6n dimensional space, 3n for position and 3n for momentum. So how am I going to visualize it? An one-dimensional oscillating system like a harmonic oscillator oscillating along a line, if you take it, the phase space would be just two-dimensional. So at every point, if we calculate the velocity, thereby the momenta, we would see that we would be able to plot the momenta against the position. At the central position, the momenta or the velocity would have the maximum value, and when it reaches the extreme position, the velocity would reach the minimum value, and it goes on with positive or negative values depending on either sides of the mean position. So this is the trajectory of or the phase space of a one-dimensional oscillating system. This is the oscillating system curve, the potential energy curve. So what could be the difference between the configuration space and phase space? So we know that configuration space gives the information only about the position. So in order to have velocity, we should have a cotangent bundle of the configuration space, which is nothing but the phase space. So the momenta are part of the phase space, unlike the generalized velocities, which were the tangent vectors to configuration space. So phase space will have a dimension which is double than that of the configuration space for any system. So if it is a 3n dimensional system, we will have 6n dimensional phase space. So what is conjugate momentum now? Let us consider a system of mass points in a conservative system. So when I say conservative system, what do I mean by that? There would be forces which could be derived from potentials, which will have only the position dependence. There won't be any velocity dependence. So in that case, what will be my Lagrangian? L is equal to, we have already studied, L is equal to T minus V. So what would be the velocity dependence of the Lagrangian? Dou L by dou x dot would be dou T minus V. So it is dou T by dou x dot minus dou V by dou x dot. So there won't be any dependence of the potential. There won't be any dependence of the potential upon the velocity. Therefore this term would be 0. So we will have only the kinetic energy dependence on the velocity. So dou L by dou x dot will reduce to dou T by dou x dot, which will be, we know what is kinetic energy, it is half mv square. So for v square we write it as x dot square plus y dot square plus z dot square. So dou by dou x dot of this would result in m into x dot. It will be m into 2 x dot, 2 will get cancelled. So it will be m into x dot, which is nothing but the momentum. So I can say that the generalized momentum associated with any generalized position coordinate qj is nothing but dou L by dou q dot j, because we got here dou L by dou x dot is equal to px. So dou L by dou qj dot would be pj. So we can arrive at the generalized momentum as the partial derivative of Lagrangian with respect to the velocity coordinate. This is for the case of conservative system. Suppose if the Lagrangian does not contain a given coordinate qj, or I say that there is no influence of this particular coordinate qj on the Lagrangian. It may contain, however, the velocity. So we don't have the position dependence of a particular coordinate. Then that coordinate is called as the cyclic or ignorable coordinate. So taking the Euler-Lagrangian equation, d by dt of dou L by dou q dot j minus dou L by dou qj equal to 0. So dou L by dou qj is going to be 0 because there won't be any dependence of Lagrangian over this particular cyclic coordinate. So in that case, what will we have? D by dt of dou L by dou q dot j alone will be there. So we have already seen in the previous slide that dou L by dou q dot j is nothing but the conjugate momentum. So pj. So it is dpj by dt, which is equal to 0, which implies pj is going to be constant. So I say that the generalized momentum corresponding to the cyclic coordinate is constant or it is conserved. So now let us get into the main derivation of Hamiltonian function. So we have seen what is configuration space, a momentum space, and then we have gone into the conjugate momentum. What will happen to the conjugate momentum for a cyclic coordinate? Now getting into the Hamiltonian function. So consider a general Lagrangian which will be a function of the coordinates qj and the velocities qjt or qj dot, which will depend upon time. So the time derivative of Lagrangian would be dl by dt would be equal to dou L by dou qj into dqj by dt plus dou L by dou q dot j. This is nothing but the qjt or the velocity coordinate dq dot j by dt plus dou L by dou t. We know that from Euler-Lagrangian equations, differential equation, dou L by dou qj is equal to d by dt of dou L by dou q dot j. So now this equation can be rewritten as dl by dt is equal to d by dt of dou L by dou q dot j into q dot j. This is going to be q dot j. So what we have done here, dou L by dou qj, we are replacing with d by dt of dou L by dou q dot j, and for dqj by dt we are writing it as q dot j. This we are keeping it as such. So what will we end up with? dl by dt is equal to adding u dv plus v du. So it is going to be d by dt of q dot j into dou L by dou q dot j plus dou L by dou t. So I can take this d by dt. So I can bring this quantity to the left hand side. So it becomes d by dt of summation q dot j dou L by dou q dot j minus L plus dou L by dou t equal to 0. So this quantity in the parenthesis within the bracket, it is sometimes called, not sometimes, it is called the energy function, which is denoted by h. So if the Lagrangian is not an explicit function of time, then this dh by dt is equal to 0, or the quantity in the parenthesis h, which is called as the energy function, will be constant. So it is one of the first integrals of motion, and it is also called as Jacobi's integral. So now that we have seen what is a Hamiltonian, h is equal to summation pk qk dot minus L. Pk is nothing but dou L by dou q dot j, the conjugate momentum. So now I'll explain the derivation of a Hamiltonian from the Lagrangian. How are we going to arrive at that? So it is a sample problem which we can use. So the Lagrangian for the system can be written as L is equal to a x dot square plus b y dot by x plus c x dot y dot plus f y square x dot z dot plus g y dot minus k into root of x square plus y square. So a, b, c, f, g and k are all constants. What is the Hamiltonian? What quantities are conserved? So this is the problem. So how are we going to get the Hamiltonian? We know already the formula for h is nothing but summation pk qk dot minus L. So summation. So here we have three dimensions x, y, z. So it is going to be px x dot plus py y dot plus pz z dot minus L. So now we have to get what is this px, py, pz. So each of this, they are nothing but the conjugate momenta. So px is dou L by dou x dot, py is dou L by dou y dot, pz is dou L by dou z dot. So upon arriving at what is px, py, pz from the given Lagrangian, we can substitute here and get the Hamiltonian. So upon substituting for px, py and pz, that is differentiating L with respect to x dot will give us the px. Differentiating L with respect to y dot will give us the conjugate momentum in the y coordinate, so py. Similarly, differentiating dou L by dou z dot, we will end up with pz. Substituting into the h, which is nothing but px x dot plus py y dot plus pz z dot minus the given Lagrangian, we would end up with this form. So here a small idea or a tip can be that we can try to see whether we can have the simplification. So we have just tried to couple the things and it seems to come in the form of Px itself, so that we can substitute in terms of 2ax dot plus cy dot plus fy square z dot into the corresponding Px. So similarly, we can end up with Pz, and then substituting all this, we end up with the answer as Pz by Fy square into Px minus A into Pz by Fy square plus K into root of x square plus y square. Remember that in a Lagrangian, we will have position as well as the velocity, whereas in the Hamiltonian, we will have position as well as the momenta. So here the Hamiltonian is conserved. What is the quantity which is conserved? The Hamiltonian, it is conserved. So now that we have come to the end of the presentation, we have learned what is configuration space, phase space, what is conjugate momentum, and the small derivation for Hamiltonian and a sample problem based on the conversion of Lagrangian to Hamiltonian. Thank you.